Okay, good afternoon, everyone. My name is William Tu. Today I'm going to talk about shared memory pool for representers. And this is a joint work with Miho and Yossi. So a quick introduction about the switch dev mode. So switch dev is an embedded switch in the NIC, right? So before we have switch dev mode, we have legacy mode, which supports only very basic stuff in the switch, like basic layer 2 forwarding, match on VLAN headers. So right now with switch dev mode, users can do much more advanced hardware flow. You can do connection tracking of flow. You can do unique tunnel of flow. So users in this case create multiple vPorts. So vPorts can be virtual functions, VF, or SF, scalable functions. And you attach this vPort to VM or container. And then you just send packet to between this VM or out of the VM, right? So ideally, all the packet or all the flow will be offloaded into the hardware, and the performance will be very good. Yeah, and there's no software involved. However, before we get to the hardware flow state, we need a software fallback, or we need a slow path control plan for that. In this figure, we can see on the right-hand side, you have a slow path, which looks like one-to-one mapping of the switch dev, right? So you have vPort on the left-hand side, and you have representer port 1, and which represents the slow path part of the representee, which is a vPort, the SF or VF. And you have representer 2, and then so with this, when first packet coming out of the VM or out of the vPort, it actually go to the slow path because your flow table, your switch dev flow table is empty. So it goes through to the slow path, the representer Netdev. And then in the representer Netdev, you can run like OVS or run Linux bridge with hardware flow enable. So OVS in this case will, with hardware flow enable, it will use like TC Flower API or use DPTK RT Flow API to insert the hardware entry into the switch dev, so that the first couple packet of the connection will be handled by the slow path, and the late coming, the subsequent packet will be handled in the switch dev, in the hardware. And today we are going to talk about the slow path part. So we have these challenges. So right now we want to create thousands of SF or thousands of VF. And when we create thousands of SF, based on the previous model, we need thousands of representer Netdev, which is also a Netdev, but it's the slow path part of the SF or VF. And this representer Netdev has its own RSQ, has its own TSQ. So two challenges here. So some NIC does not have enough hardware queue. So for example, ICE support only up to 1K hardware queue. So the queue is not enough. And the second is when you are running a smart NIC like Bluefield or IPU, it doesn't have enough memory, right, to just handling 1,000 Netdev. Or for example, we only have 16 or 32 gigabyte of memory in the Bluefield. So memory is another issue. So the question we want to ask us is, if the slow path is just to handle the first couple of packets and to do offload, do we need so much resource, and can we save some resources somewhere? So we come up with these two solutions, and here I have three designs. So the design 0 is the current one, so nothing. So we will have dedicated one-to-one, one representer Netdev per SF. The design 1, we call it share RxQ, and the design 2, which solve the problem of memory, is called adjustable RxQ for the dedicated representer Netdev. So let's talk about first the design 1. So design 1 says, because we don't have enough hardware queue, right? So just don't allocate RxQ for the representers. So in this figure, you see that packet comes in, it should goes to the representer 1 or representer 2 and port, right? But don't go there because I want to save memory. Just there's no RxQ there. So redirect all the packet to the single share RxQ. Maybe it's on the PF or maybe on the uplink representers, so that it saves queues and it saves a lot of memories. And the same logic applied to the TX. If you want to save more, like so, all the packets sent out from the representer just use the uplink, use share TXQ, for example. So this model has been implemented today by drivers such as ICE, NFP, and SFC. So huge memory saving, and if you increase your representers, you still use constant memory, right? However, there's a problem, like it's because you are sharing this RxQ, and then if one VM is running something like DPDK packet gen, another VM is runs like ping, then it's easier to see that the DPDK running VM consume when it hits the slow path, it consumes all the entries, all the RxQ buffers of the shared RxQ. Basically, another VM, the ping running VM doesn't get any bandwidth at all. So we have a performance isolation problem. And we do think about how to solve it. So in the switch dev or in the hardware, we have like DC policing of load, we have shaping and back pressure. However, it's doable, but it's getting pretty complicated because remember the slow path is trying to be the software fallback of the fast path. So the behavior of the two should be the same or similar, right? So if we want to apply something there, first thing is we want to somehow steering the traffic or identify the slow path traffic, which is not that easy. So then we talk about the second challenge, which is the memory problem. So the first question I want to know is when I create a representer Netdev of MX5, like how much memory does one device consume? And there's no good tool for doing that today. So what I did is I just create so many SF representers. I create 200 of them, and then I set up its RxQ, so 1Q, and with Q depth to be 1K, and then bring up the device so that the page pool will really allocate the page. And then I just get memory difference of the whole system, and then take average divided by 200. There are other memory metrics. For example, you can get firmware page numbers from the MX5, and also you can get the page pool used by a particular device or for a particular NAPI ID. So for example, you can get, in this case, you can get like I have index 10, and then it consumes like 1.8 megabyte of memory here. And the result shows that with the configurations of one channel, one RxQ, and Q depth of 1K, it consumes about 2.8 megabyte of memory. And I want to break down, like, okay, you consume 2.8 megabyte, what's the breakdown? So among the 2.8, about 1.8 is consumed by page pool. And we know that the page pool is used by RxQ. So I know that with RxQ 1K, it consumes 1.8 megabyte. And there's like firmware consume and others. And here we also know that if I increase my queue count to channel count to 2, it's almost double from 2.8 to 5. And another thing to look at is if I decrease my queue depth, the RxQ depth from 1K to 500, then it pretty much like drop from 2.8 to 1.8. So it decreased because of the page pool. We are using less page pool memory there. And the other way around, if we increase to 2K, it increased to 4.9. So the question is here is that if we want to save memory, we want to save memory because we don't have enough memory. Like, can we allocate less RxQ buffer? Like how important it is, right? So a little bit background of the RxQ buffer pre-allocation. So ONIC today has multiple RxQ. It's a circular ring. So when packet comes in, it consumes a buffer in the circular ring. And we have NetDev port receiving the packet, passing up to the create SKB and passing up. And after that, we'll go to the page pool and allocate more page and refill into the ring. And this ring depth is very important, and we are using it for 3 reasons. First, we don't know the packet pattern, right? So packet might come in a burst, so we need a huge buffer to absorb the burstness. And also, we don't have a fixed per packet processing time. Like if a packet is ping, if a packet is TCP, a packet is TLS, then the processing time is definitely different. So there's jittering there. And then also there's a scheduling delay. Like packet comes in, we need to have interrupt and kick in. And there's a delay there. So we need a buffer. So a quick evaluation using 2 machines. So we say that we set up 2 servers, and then there's a DPU in between, and I disable OVS so that all the packet goes through the slow path. And then I try to just set up the RxQ depth from 64 to 2K and see how the performance varies. So you can see that larger Q depth definitely works better, right? Going from 64, it drops to 3 something, and then by 12 or 1K, it goes to 6 gigabit per second. But the problem is, the question we want to know is that, what if there's no traffic? So if there's no traffic, then we still have a lot of buffers there and waiting for the burst, right? So can we do better there, or can we do something to optimize it? So this is how the driver currently works, right? We always have 1K buffer. We receive, and we always refill to the full RSQ depth. We always refill to the 1K. And the idea of design tool, which try to save memory, is we want to dynamically allocate the buffer. So we set up 2 values. So the first value is called low watermark. So low watermark, let's fix it to 128. So 128 entry, 128 buffers. Another value is high watermark. So high watermark is just the value you set by is2-g, the queue length. And then we want to say, when driver just initialize minimum, or just 128. And then when you are processing the packet, you just somehow allocate buffer between them. Don't always go to the high watermark. Just do something there before that. Save some memory there. So a simple algorithm is just to do this, like when I have a NAPI receive, and then it's an interrupt mode, meaning I'm processing packet less than the budget. Then I want to save memory by just passing the packet, and I don't want to allocate more memory, meaning I don't want to refill, so that we are saving memory, right? We don't allocate more memory. And when we found that it's in the NAPI busy state, which means I use all the budget, then I want to fall back to the original design. I try to allocate to the full RSQ length, so that we can minimize the performance impact. So this design, the first thing we found that this design, the first burst packet over 128 will definitely hit some packet drop, right? Because we don't have so many buffers there to handle it. But after we detect that, we'll quickly catch up. We'll say, okay, we allocate more, we allocate up to 1K, for example. So this figure shows the comparison, right? The blue one is a static one, which just is static. And then the orange one is the adjustable one, which implements the simple algorithm I mentioned. So that we do see, I didn't show it here, but we do see more packet being dropped because of this first packet over 128. But then the overall performance difference isn't differ a lot. I would say within 5% difference. I guess the reason is might be like when we are running TCP, it's like slow start, and when packet drop, it tries to ghost down or something. Yeah. So with that design, we can save some memory by not allocating so much memory per every time we receive packet. So the second design, however, it's not good enough because we found that if you want to create 1,000 devices, and then the late coming device might still not having enough memory, right? Because the first couple hundred might use all of them, and then the late coming representative still don't have enough memory. So we want to see if we can create a shared page pool, and this shared page pool provides a page for all the representative Netdev. And this is doable because all the representative Netdev, they are sharing one DMA and one DMA. So you don't have to map or unmap different pages for them. So it's the same one. And so for example, in this figure, we can have something like primary representative of PF. Initially, it creates this shared page pool. And when we create more and more representative Netdev, it just it doesn't create its own per queue page pool, but it just requests the page from the shared page pool. So remember, we have this issue that once we have anything shared, then we have fairness issue, right? So maybe one of the representative device having DPTK, running DPTK, and then it's going to use all the shared memory pool. So we want to enforce some fairness layer between the page pool and all the users, the representative Netdev. So that when someone is using too much, I want to say, okay, no, this is your upper limit. Stop requesting pages. So now the problem is very similar to the hardware switch today. So we borrow the idea from there. So in a hardware switch today, we have a fixed shared buffer, and we have multiple output port. And packet comes in, they all use this shared buffer. And the idea there is that they want to have some kind of fairness. So they have this idea of logical queue per output port. And then there's a paper describing a mechanism called dynamic threshold, which is this formula, saying that for every particular port at any time, the maximum utilization of the shared buffer is this value, so that it guarantees somehow the fairness between that. If you are using over your own maximum utilization of your port, then I'm not going to give you more memory from the buffer. And think of this problem as our problem. So the output port is like our RxQ or our representative Netdev, right? The logical queue in here is like our RxQ, and the shared buffer is the shared memory pool we are talking about. So far we talk about design 0, design 1, and design 2. And each vendor driver has different implementation, right? So here is a summary, and I want to see if we can have a DevLink interface so that allowing users to do configuration based on their use case. If users care about memory or utilization, or they have limited number of queues, then use the shared RxQ. It's very efficient. Like you use only one queue or a couple queues. If performance isolation is very important and they don't want to have the fairness issue, then you can use dedicated case, the design 0, or use the adjustable RxQ, the design number 2 or number 3. So we can say, okay, the mode is none means, so this table summarizes the current state. So for example, the dedicated representative Netdev right now is used by the Marvell driver and also the MX5 driver. And the basic model, which has shared RxQ, is used by ICE and Broadcom and NFT and SFC. And the new design, we haven't implemented yet. Yeah. So more performance evaluation. So here we want to run Apache benchmark. So here we set up 2 machines connected back to back, and for each machine we have 1 vPort, and we're running like iPerf and Apache AB benchmark. The traffic goes through OVS, and OVS we disable hardware overload so that it can go through the slow path, exercise the RxQ, different RxQ set up in the representative Netdev. and then we measure the performance. So we run Apache AB, we create 1 million requests, and with 100 concurrency level. We disable hardware flow. So we have these 4 metrics to measure. So the first one is time to complete, of course, important, right? Because we want to know how many total times we can finish the 1 million connection. Out of buffer means the number of packet being dropped when there's no RSQ buffer. So remember, we're tuning different RSQ buffer from 64 to 2K. So yeah, so it's important to, so, and this is a matrix, this is the counter, we have to get it from the driver. Request per second is average HTTP request per second. And also the connection time, this involves the connect process and waiting time for the Apache AB. So the first result shows that the first column we see is that the time to complete pretty much the same after we have 256 queue size. It's like 24 seconds. However, the out of buffer is decreasing, which makes sense, right? Because when we have only 64 queue depths, then a lot of packet will be dropped because there's no buffer and we are not refilling the buffer fast enough. When you have 2K buffer, then or 1K buffer, we have 0 out of buffer. The request per second is similar. The connection time is similar after the 256. Then the connection time standard deviation differs because I guess it's because packets are being dropped more, so that the standard deviation, the jittering is higher. So that's the static one. And for this one, we are comparing the static RSQ size from 64 to 128, compare it to the simple algorithm we mentioned, the adjustable RSQ, which has low watermark and high watermark. So first we see that the out of buffer case, which is the packet drop case, the adjustable one is higher, which makes sense because remember in the very beginning we only give it 128 buffer. So the first burst of the packet over 128 will definitely be dropped. So and also the standard deviation of the adjustable design is higher. I guess this is because of the drop. Otherwise, the performance, for example, time to completion, the request per second or connection time is pretty much the same, and the impact should be lower. And remember, in this case, although we see some performance difference, but this is the case when we disable hardware flow because we want to exercise the slow path. So all packet goes through hardware flow. All packet goes through the slow path. In the production environment, we should see much less traffic because we enable hardware flow. So only the first couple packets will hit the slow path. So ideally, we should see even less performance impact, but it's hard to like find a real good test case here. Not a benchmark here. So in summary, today we talk about the switch dev, the slow path and the fast path, right? And then we are saying that, okay, because we want to scale to thousands of devices, we hit these 2 issues, not enough queue and not enough memory. And we look at the existing device driver, we say, okay, most of then implement the design 1, design 2, which has shared RQ or dedicated RQ. And then we say that maybe we can save some memory by not allocating so much RxQ, and then that's the first idea. So driver vendors not allocating so many RxQ. And the second idea is maybe you can use the shared memory pool so that we can kind of organize the system, all the devices, memory utilization in a system-wide way. And we have this attribute to set up for different pool, the shared memory pool mode for the different device. We have more performance number and design in the paper. So that's all I have. Thank you.
So thanks for the presentation, really good. I like that you're working across companies, so thanks for working with us. I have a comment about like you're doing a lot of traffic, and in fact, we've looked at something similar in the past a little bit, not done as much work as you did towards it. I think it really makes a lot of sense at the descriptor numbers that you called. I thought it was funny that 512 looked like it was one of the better ring sizes.
Oh, yeah. Both sides?
Testing, there we go. Can you go back a few slides? So a couple of comments, couple more to the three modes you had.
Oh, yes, yes. Okay.
So one of the things you listed as a positive about the design zeros that you're not sharing, except for when you get to more queues than CPUs, you're sharing again.
Yes, yes.
So one general thought, it seems like the best of both worlds would be to design one with the number of queues equal to CPUs in terms of what's shared for the RX queues. Have you given that any thought?
Yes, yes, yes. So in this case, for example, for Bluefield, we have 16 queues. So the maximum is like sharing 1K representers for the 16 queue. So it's still possible to hash, for them to hash the same RX queue, right? So,
yeah, that's what I was kind of getting at, because it's like, okay, we have the sharing case, and it's, well, yeah, but if your number of queues exceeds CPUs, you're back to sharing anyway, because they end up in the same snappy context. The other thing, in terms of the logic you were using to reduce the queue size, to me it seems kind of backwards in that when you go into interrupt enabled mode, you essentially need some skid room. So that's when you should have your maximum queue size. And when you're nappy busy, it would make sense there to go ahead and roll it back down to 128. Because if you can't keep up with the current workload, you're going to be overrunning anyway. And so, I don't know, that just seems like something you might want to try testing for this, because I've actually been asked to do this kind of implementation in the past. It actually does show better performance, because in the case of if you're locked into polling, you actually reduce your overall memory footprint and poll faster as a result, just because you're pulling on fewer pages and buffers. So.
Oh, that's interesting.
Yeah, because it reduces it and makes it more cache efficient.
Can I interrupt? Andrew, I'm sorry. I guess you get to ask the last question.
The only comment I had for you actually wasn't even a question. I just wanted to say, I think you should look into cache residency counters on the CPU and look at the rings and what your different sizes do with the cache behaviors. Because I think you're actually probably starting to get to the point where your cache is being more efficient with those ring sizes, where you were starting to see the hot performance has to do a lot with cache.
You mean the ring, right? Not the page, right? The ring might be smaller ring size, maybe fit into the cache, so they perform better.
We've seen it, like when you're doing streaming workloads with small packets, 256 is really good.
Yes.
Anything bigger, not great. Anyway, thank you.
Thank you. Got it. Thank you.